All right, wait a few minutes. Looks like no one's hopping in here live, which is fine. This video will be up here all week. So where would it left off? Last class. Let's see if I can get this going here. Was we were talking about how do we build confidence intervals, and then today we'll talk about how do we do hypothesis testing for examples where we have two sample means and we only have sample variances, right? So we built out this confidence interval equation last class where we said we build our confidence interval still around whatever sample difference we find. It's just that now that we only have sample variances, we have to use that student t distribution to find the number of standard deviations away that we want to go to get our upper and lower bound. And then our standard deviation of that difference in sample means is now going to be the variance kind of each sample mean added together, and then we want the standard deviation, so we take the square root. Okay, so we worked through and then how many degrees of freedom? Yeah, so this was where we said, look, there's this really complicated way to find degrees of freedom when you have two populations. It's not simply n-1. I'm not going to make you do this. I'll always give you kind of the assumed true degrees of freedom. And actually, after the video, I'm going to get an announcement up for the homework. Since we'll have covered the material, I'll give you what the degrees of freedom should be on the questions on the Connect homework, since it kind of expects you to calculate them. I don't want you to have to spend all that time because this is a hard equation to use. So we kind of talked about the steps last class. We saw how we do this in Excel. It's really the exact same thing we were doing with confidence intervals for one population, with just a few more moving parts, right? When we had only had sample variances, we then had to use that student t distribution. So we had a couple, we'll work through a confidence interval one pretty quick. I'll then work through a hypothesis test example pretty quick, and then we'll see how we do this in Excel. Also, after today's, I'll splice together all the Excel stuff we've done up to this point so you can kind of have it all in one place and have a separate video for that. So let's assume that we had texters and non-texters, right? And I want to know, is there a difference in their response time when they're driving? So I take two samples, one of 49. Those are what? My non-texters. 64 texters, and then I measure their response time, maybe how quickly they brake or something. And then I also have the sample variances. So if I want to build a 90% confidence interval for the true difference between texters and non-texters, so let me blow this up here for a second. All I'm really going to do is grab the values and plug them into my confidence interval equation. So the difference in sample means that I found was, oops, there we go. So my first sample mean, I want to go this way, everything's reversed for me. So here's my non-texters minus my texters, right? That's what I'm looking for. So I had what? 1.3 was the texters. And then if I come down here, okay, well, we're gonna have to move this cat. Hey. Get off. All right. Sorry about that. Doing this from an undisclosed location here. So we've got the difference in my sample means, and from there, I'm going to need to add and subtract some t value, right? I would have to give you your assumed true degrees of freedom here, so I'll show you that in just a second. And then we multiply by, oh, looks like someone hopped in here. Let me switch it. There we go. Oh, I guess I decided to leave. So from here, it's just a matter of taking each group's variance over that group's sample size. Okay. So there we have what? 0.16. All right, back in. Let me pin my video now. Back and shoot. Oh, there we go. So 0.16 over my sample size of 49, and then 1.44 over my sample size of 64. All right. So the only step I have left to do is really look up that t value. So if I want the 90% confidence interval, my alpha is 0.1. So I'm going to have to look up alpha over 2. So if I divide this by 2, I've got 0.05. So from there, I would have to give you what that degrees of freedom is. So here, if I plug everything in and calculate that for you, I end up with a degrees of freedom of 80. Okay. So from there, scroll down. Where is it? Oh, it's not on my Google Drive. It's on thumb drive. So we want to open that. Pass the version. We want to open my student T distribution, right, my T tables. Rotate them so we can see them. And then there we go. We zoom in here. So we wanted 0.05 and we had degrees of freedom of 80. So we're going to scroll down here. This is the 0.05 column. My degrees of freedom is 80. So 1.64 or no, 0.664 is my T value there. From there, it's just a matter of kind of getting this entered in my calculator. Right? So it's the exact same equation that we had before. There's just a few more moving parts. So once we identified everything and we had our degrees of freedom, which in practice, I will give you this, or I would have told you, assume the degrees of freedom is 80. Well, then we had everything we needed to plug into that lower and upper bound equation, and we get this range of negative 1.33 to negative 0.79. Okay. So actually, I'm just going to stop share here. So what I can say with 90% confidence, remember, because this was my 90% confidence interval, is that the true difference between texters and non-texters is a negative value. So that would imply that the response time from texters is higher, right? That's the only way that difference is a negative value. So with 90% confidence, I could say that texters, right, are a little bit slower in terms of their response time. Okay. So someone's joining me here. Hopefully it's connecting okay. And they left. So I'm wondering if something's not wrong with the link. All right. So we got our confidence interval. We could also build. So you know, we found that it was only negative values, right? So 90% confidence, we could say that the second group or the texters had a longer response time, right? Or a higher value for their response time. So that was kind of how we interpreted that interval. From there, I have another example in here. We're not going to work through this one, but it may be some additional practice that will be good, right? If we had brand A, brand B cigarettes, and we wanted to test for whether or not there's a true difference in their nicotine levels, we take a sample of 20 of the first one, 25 of the second cigarette. We could do the exact same thing. So here, you know, I don't want to work through necessarily plugging all the values, and I think that's fairly easy given all the examples we worked on up to this point. But one of the hard parts might be kind of looking up that T value. So this would be a good one where I said it's the 95% confidence interval. So my alpha there is 0.05. Okay. So if my alpha is 0.05, alpha divided by 2 should be 0.025. Okay. So that's the area that I want in each side of my confidence interval. I'm given this assumed true degrees of freedom of 42. Okay. So we'll go to our T table. We've got the area that we wanted was 0.025. My degrees of freedom was told me to be 42. So 2.018, right? So that's how I'm getting that T value here, right? Everything else is just a matter of plugging in the sample means, the sample variances and sample sizes, which we were given in the problem. Once we looked up that T value, then it's just a matter of getting these entered into our calculator, okay? So this one, once again, I've got only negative values. Notice my confidence interval starts at negative 0.4, stops at negative 0.13. So with 95% confidence here, if I set this up, I believe it was brand A minus brand B. Yep. So with 95% confidence, if the only values that difference could be are negative values, I could say that brand B has higher nicotine levels. All right, so I can start to make some statements about, you know, comparing groups means basically. All right. So moving on, oops. What if we wanted to do hypothesis testing? It's going to look exactly like what we've been doing, especially when we had those two population mean examples. It's just that now, since we only have sample variances, right, we're going to have to use the student t distribution to look up p-values and critical values, right? So our test statistic looks exactly like it did before. It's just that now we've only got sample variances instead of population variances. So our test statistic is no longer a z statistic, it's a t statistic, right? A test statistic coming from a student t distribution. The assumed true value here, I'm still going to use 0, just like I did in the other examples. And then if we need to find our degrees of freedom, it's that same equation. But once again, I'll be giving you these assumed true degrees of freedom. So let's say we wanted to test for whether or not male and female doctors have a different starting salary or a different salary. I don't know if it's starting salary here. But we take a sample size of 41 of each, and we find the sample means for both groups, and the sample variances we calculate as well. So if we're thinking about the difference between men and women here and whether or not they make different salaries or have different values for their salaries. Go to a new sheet here if I can get my fingers to work. So what I'm thinking about here is I want to take male minus female physician starting salaries. This is going to be like my sample difference. Okay. If I just want to know, are they different from each other? What I'm really saying is, are these two values different? Which if I move the mean for females over by subtracting it from both sides, and I said equal here, I'm saying that not equal to each other. What I'm really saying is that difference anything other than 0? Right? That will be my alternative hypothesis, which then means my null, and usually we write it above, but it's okay to write it below it as well. That means my null would be that difference between the two is exactly equal to 0. And here, I'm not really thinking about my sample. This isn't quite really technically correct, because really our null alternative hypothesis would be for the true population means differences, right? Or the true difference, not the sample difference. I was just kind of using this notation to kind of think about what we're going to be comparing in this problem. Right? So we've got the null hypothesis, which is that this difference is equal to 0. So we're going to have C here. Oh, maybe I thought I had there we go, a little graphic there. If we wanted to find the critical values, it's just like we were doing before. It's just now those critical values come from a student t distribution. So if I've got the 1% significance level, so my alpha there is 0.01. So what I'm thinking about is I've got this student t distribution. I've got a two-tailed test. So the total area in the tails is my alpha value of 0.01, which means there's half of alpha in each tail. So the areas that I want in the tail are 0.005. And I'm going to have a pair of critical values for this two-tailed test. Okay. So if I go to was given my assumed true degrees of freedom to be 80. So we wanted 0.005 in that tail, all the way down here, degrees of freedom of 80. So 2.639 positive and negative, right? Because I've got a two-tailed test here. So I've got two critical values. Okay. Well, now that I've got my critical values, go back here. So got my critical values. Now I'm going to find my test statistic and plot that against my critical values, right? So really, this is just a matter of once I have that equation in front of me, I'm plugging in the sample sizes or sample variances, sample sizes, sample means. The assumed true difference we're using is always going to be 0. I get this obnoxiously large test statistic of 22.92, right? So if it was that large, right, that's going to be somewhere like way over here, which is, clearly in one of my rejection regions. So I would say here I reject. Okay. Now, if I wanted to use the p-value approach and just kind of find the area to the right and then multiply it by 2, it's going to be very difficult to do that by hand using the student t distribution unless I give you exactly one of the values that's in that student t table. So notice if I tried to look up my p-value here at degrees of freedom of 80, the highest test statistic I have is 2.6. So how can I find 22? Well, here, all I could really say was, I know the area to the right of 2.6 was 0.005. So if I multiplied that by 2, that would be 0.01. So if I've got a test statistic that's even more extreme, all I can really say is the area to the right multiplied by 2 is going to be less than 0.01. Now, I know it's going to be pretty close to 0 here, just because of how large that test statistic is. But even if it was like 4.9, I don't really know exactly what the p-value is. All I could say is that, well, I know this area has to be less than 0.005. I'm going to multiply that by 2, so I know that it's going to be less than 0.01. So I won't ask you to kind of put the p-value in a range like on the exam. I think some of the homework connections, it does have that. So for instance, if I had a test statistic of 2.5 here, well, I would know the area to the right of it would be somewhere in between 0.005 and 0.01. Okay. So if the area is in between 0.005, so this area, if I had a test statistic, of 2.5, I know that area would be somewhere in between 0.005 and 0.01. But remember, the area for a two-tailed test in this tail is only half my p-value. So then for my total p-value, I would multiply both of those bounds by 2. And all I could say if my test statistic was 2.5 was that p-value is somewhere in between 0.01 and 0.02. But on the exam, I won't expect you to do that for the sake of time. Like if I gave you on the exam and I gave you an assumed true degrees of freedom of 80, I would have it so that the test statistic worked out to be exactly like 1.671. Okay. All right, I don't think anyone else has joined in here. So we're now going to take a look at, no, actually, I think I had a grade meme maybe here at the end. So 99 problems, but right, rejecting the null one. Although I think we could reject the null here. So this meme doesn't fit, but I liked the meme, so I threw it in here. Right? Now we had been working on a file. I've been kind of saving it as we go along here. Now this should be pretty easy because I think we did the confidence intervals. Close this. Oh, I don't want to help. I want to close. Okay. So come on. All right. So we had our confidence intervals. Also, I was looking, I looked at this last class. So the whole reason why I couldn't get the confidence.t to work is because you can only do it for one population examples. Because what it does is it's using that sample size to calculate your standard deviation on the sample mean. Right? So when I was putting in the standard deviation there of our sample means, what I should have been putting in was the sample variance of the original variables. The problem is I can only put in one of them. So we can't use that confidence.norm or that confidence.t for these two population examples. I said you shouldn't have been using it for one. I just noticed that some people were, and they weren't quite using it correctly. So I'm not going to waste time kind of going over that because for the sake of this assignment, you're not going to be able to use those built-in functions anyways for a two population example. So when you're working through the homework, you should set it up like I have, where you kind of find the t-value, you find the standard deviation of your sample differences, and then you just kind of use Excel to be your calculator here to find that upper and lower bound. Okay. So here, I think I was playing around with the values. We'll change this back to 0, where I've got a two-tailed test. Okay. So I think what I had here was male and female BMI, and all I had were sample variances. So we could test to see, is there a difference, right? We looked at that with confidence intervals, and we said that we couldn't quite say at the 99% level that there was a difference, right? Because it had positive and negative values. But let's work through and find it using, or do some hypothesis testing, whether or not we can reject that true difference is equal to 0, okay? So the first part is going to be, basically we just have to use Excel to be a calculator. We have that test statistic equation, right? Which is, we're going to take the difference in our sample means. So male minus female. Now here, there we go, all right? I would then subtract that assumed true difference, which is 0. But since I have that in a cell, I'm just going to put that cell reference so I can show you, in the real world, like what if we wanted to test against values other than 0, right? I'm going to simplify it for us and it would always be 0. But what if I wanted to do something different? I'm then going to divide this by, and if we remember, what's in the denominator here represents the standard deviation for the difference in our sample means, right? But we actually can double dip because we already found that for our confidence interval, right? So we can use this standard deviation of our sample means that we calculated, oh, where was it? Up here somewhere, right? So we're dividing by that standard deviation of our sample means, and that way it just makes it a lot easier. I don't have to type this all into one cell. So I hit enter and I get my test statistic. So it's about negative 2.36, okay? So I've got my test statistic. If I wanted to find my p-value, remember what I'm doing there is, I'll put this on, just redraw it here. If I wanted to find my p-value, what I would do is take this test statistic or t-statistic I found of about 2.63. I want to find the area to the right, but it's a two-tailed test, so it would have been equally as likely for me to see something over here. So once I find this area, well, we got someone coming in a little bit here, so I'll pin my video here real quick. So once I find this area, I basically multiply it by 2, and that would leave me with my p-value. Okay. So go back to Excel. All right, I've got that test statistic. Oh, I actually had a test statistic of negative 2.36, but that shouldn't change anything, right? It actually just makes it easier because now I just find the area in this lower right tail and multiply it by 2. Okay, so how do I do that in Excel? Well, I go here, equal sign. I use that t.dist, all right? So my t.dist, I tell it my test statistic, comma, I tell it my degrees of freedom, which I had kind of pre-built in here. Right, here's my degrees of freedom. And then comma 1 is going to give me the area to the left of that test statistic, which is what I wanted. But then I need to remember, I need to then multiply it by 2. Okay. So here, I'll multiply whatever that t.dist function returns to me by 2 to get my p-value. Okay. Now I can also use, and here I've got the critical value here, but that's not, this isn't labeled correctly because I put things in different. I want to show you multiple ways to do this p-value. So the other way you can find the p-value, if I use t.dist.2t, this will basically do exactly what the t.dist function does, but it'll multiply it by 240. So if I tell it my test statistic and then comma, tell it my degrees of freedom, it'll find the area that's more extreme than my test statistic and multiply it by 2. Now the problem is this function was created in such that it only accepts negative, or sorry, not negative, it only accepts positive test statistics. So if I hit enter here, it's going to be mad because I've got a negative test statistic and it always is kind of using that right side of the student t-distribution just like the tables do. So if I want to use that .2t, which honestly, it doesn't save me a lot of work, right? It's basically the same thing as t.dist. It just multiplies it by 2 for me. So here, if I do want to use that .2t form of it, whatever my test statistic is, I have to make sure I'm just telling it the positive value of that. And that's really okay because for a two-tailed test, right, it's kind of like we only see one of these test statistics, but I could look up either one of these areas and multiply it by 2 and it's symmetric, so it'll give me the same value. So here, hit enter, and now I've got that exact same p-value as I did before. Okay. So I see join here, Zach. If you have any questions, feel free to unmute and ask. But I'm just kind of finishing up on this this Excel. So if I wanted to find the critical values here, well, that was where I knew the alpha that I wanted in the tail, and I want to find the corresponding t-value that gives that to me. However, just like with the one we worked through by hand, I'm going to have a pair of critical values because alpha total is in the tails, which means there's half of alpha in each tail. Right? So we'll go back here. I know that I want alpha over 2 in each tail, and I'm using a student t-distribution, so I'm using t.inv. Right? I'm working in reverse or the inverse. I know the area in the tail. I want to find the corresponding t-value. So I'll take alpha divided by 2, comma, I have to tell it my degrees of freedom now, which I had in this cell up there. Now this should give me the negative critical value. And I know that I'm going to have a pair of critical values where they're the same value, but one's negative, one's positive. So I use the absolute value there. I can kind of show here or signifying that I've got a pair of critical values at each alpha here. If I then want to find my critical values at the next, like the two, other confidence intervals, not confidence intervals, confidence levels, right? Alphas of 0.1, 0.05, and 0.01. I'm going to copy this down, but I have to remember, oh yeah, I don't want that degrees of freedom cell reference to change. So I'm going to freeze that. Now, when I copy these down, it should update the alpha, but not that degrees of freedom reference. So I've got my critical values pretty quick here. If I'm looking at this, if I tried to plot the test statistic against these critical values, it'd be in the rejection region, or it's more extreme than the critical value at the 90 and 95% level. So with 90 and 95% confidence, I could say that there's a difference in male and female BMI, but it's not quite larger than the critical value at 99%, which is exactly the same conclusion we got from the confidence interval, that this value of 0 with 90 and 95% confidence, we could reject that as the true difference, right? But not quite at the 99% level. And then the p-value would make, lead to the same decision. It's 0.01. We said we only reject if that p-value is less than alpha. So if our p-value is 0.018, that'd be less than 0.1 and 0.05, but not quite if 0.01, if alpha is 0.01. So we get the same kind of rejection decisions. And with a two-tailed test, the outcome of like whether or not that difference is 0, really, it's just approaching it in a different way, but it's allowing us to be able to say whether or not that true difference could be 0. If that value of 0 is in my confidence interval, then that could be one of the true differences, which means I should be failing to reject the null. Sure enough, when I can say that 0 isn't in my confidence interval, I can actually reject this assumed true value of 0 for the difference. But when 0 is in my confidence interval, well, then for my hypothesis test, I'm going to fail to reject that this could be the true difference. So it's good that those decisions line up. It's a little bit off for a one-tailed test, but as long as you have a two-tailed test, you should get the same, you basically think about for every value in your confidence interval, if you do a hypothesis test for it, a two-tailed test, you'll fail to reject any assumed true difference that's in this range. For instance, let's try to do -0.3, right? That's in all of the confidence intervals. We should fail to reject that at every level. So what, -0.3 here. Sure enough, I've got a huge p-value, right? I'd be failing to reject at all of these levels. And I could go through and do this hypothesis test for all of these different levels. And anything that's in my confidence interval, if I do a two-tailed test for it, I will fail to reject those. Whereas if I do something outside that range, so let's do something like 0.3, I should get a really small p-value because 0.3 isn't in any of these intervals. So I should be rejecting 0.3 if I make that my assumed true value, right? Which sure enough, e to the -0.05 means move the decimal place 5 places to the left. So this is a p-value of pretty much 0. Okay. All right. This video went a little longer than I thought, but I want to do one more thing and we'll kind of close it out, right? So there's a built-in shortcut in Excel. So I'm going to change this back to 0 for a second, which is this t.test function. So instead of calculating the sample mean, sample variances, sample sizes, doing all the work, what you could do, so here, that first array, I'm going to select male BMI. Okay. And then here, I'm going to use this one and put a comma. The second one was this female data, which was on a different sheet. So I'm going to select that. Okay. And then I'm going to put a comma. I'm going to go back to the male data. I don't want that reference in there, so I'm just going to delete that real quick. I just want to show you as I'm typing this function out. So I select my two variables that I would have used to calculate my sample means. This then reminds me, okay, those were the first two things you selected. Now, how many what tailed test is it? We're doing a two-tailed test. And then what type of t.test do you want to do? Well, we're only ever going to use 1 and 3 here. Okay. 1 is what we'll talk about Monday when we return from break. The examples we've been working through when we have 2 samples and they don't have the same sample variances, right? Which is like every, how likely would it be that they have the exact same variance? Not very likely. So our type here is that third one, or a 3, right? Where we have 2 sample means or they don't have the same variance, okay? So what this does is it calculates the sample mean, sample variance, and sample sizes behind the scenes, calculates your test statistic, looks that test statistic up, finds the p-value, depending on if it's a 1 or a 2-tailed test. It follows the procedure differently for a 1-tailed and 2-tailed test, and then it spits back out at you that p-value. Notice here, I could probably, if I formatted these, right, you'll see they are the exact same value, just they're formatted differently. So it gives us the exact same value we were finding using the kind of longer method, right? It just does a lot quicker and does it all behind the scenes. So why am I even teaching you or showing you the other way? Well, because that T-dot test can't really work with proportions. So we went through a proportion example. It's not able to deal with proportions. And then also, if I want to do any other value other than 0 as my kind of assumed true difference, notice it can't recognize any other value it's testing against other than 0. So if we do have, this assumed true difference of 0, that T-dot test can save us a lot of time. And, I'm always giving you those assumed true differences of 0. So it does save a lot of time. But anytime you don't have it in the real world, it's not always going to be 0. If you want to test against other values, you can't use that T-dot test, unfortunately. You have to know how to kind of use Excel to be a calculator, calculate your test statistics after you found the sample means, variances, and sample sizes, and then using that T-dot dist or T-dot INV to find your critical values and your p-values. Okay. All right. So that should wrap it up on my end. If you have any questions, Zach, before you get out of here, I'll be posting this video up on YouTube. Like I said, I'll splice together the Excel with all the old Excel so that you have that all in one place. Other than that, hopefully, if you're watching this after the fact on over Thanksgiving or something, hopefully you're having good holidays, and I will see you guys back in class on Monday.